All right, so we are back, and as I had mentioned at the end of the last video, what we're going to focus on in this video are um, some useful formulas, and also we're going to go over some examples of how to apply those formulas. So let's first take a look at the simple interest formula. Um, as I had mentioned before, option number one that was offered to Alfredo in the previous video is an example of a simple interest account or an account that earns simple interest. So let's take a look at the equation for simple interest. And we'll also talk about how it is actually just a linear equation kind of in disguise with different variables. So here are the formulas. A of t equals P plus P times RT. Or you could also take out the greatest common factor of P and write that as A of t equals P times the quantity 1 plus RT. So the variables in this case represent A of t is the amount of whatever it is that you're working with, whatever quantity you're working with, after a certain amount of time. P is the initial amount. If we're talking about money specifically, it's typically the principal amount. T is time that can be measured in months, years, but again, it's going to be constant. And then R is your interest rate or your growth rate expressed as a decimal. And that's really super important here is that your rate always needs to be expressed as a decimal in these scenarios, or you're going to get really ridiculously either large or small answers. All right, so let's kind of break down this equation, and I'll show you why it's actually linear in nature. So A of t just represents your output value. So if we're thinking about a linear equation, your output values are typically represented by the variable y. P, the principal amount, is your initial amount. And typically in a linear equation, the starting amount or the initial amount is the y-intercept. It's whatever your output value is when x is equal to 0. So that's B. P times R is just your initial amount times whatever your interest rate is. And that's going to be, like in this case, the constant amount in which your account grows. So that's like the slope. And then T, time, that represents your input values, and your input values in a linear function are typically represented by x. So really, it's just y equals mx plus b written as y equals b plus mx. Okay, so this is just, again, a linear equation. Now, how would you apply this equation? Well, you can use it for a variety of different ways. Most of the time, we're going to be looking to see how much money is in an account after a specific amount of time, or we might want to solve for one of the other variables if we're given other information. So if we look at the Alfredo problem, option number one, we're given a whole bunch of information, and you can go back and look at this while you're going through this. This is really just on page one of our notes. The principal amount that he's given, the amount that he starts off with, is $1,000. He's offered an interest rate of 7%. So the interest rate is 7%, but we always want to represent that as a decimal. So we're going to have to take 7 and divide that by 100, and that's going to be 0.07. Okay, so that's our rate. So our rate is going to be 0.07. And we're really not given a specific time, so that's kind of a question mark for now. But what we'll do is we'll go back and we'll evaluate this function that I'm about to write for a specific amount of time, so we see that the function actually works. So let's write the function out. So the function is A of t, so we don't know the amount that's in the account if we don't know what the time is yet. We do know the principal value is 1,000, plus the initial value again, times the rate, 0.07, and then times the time. So if we simplify this down, again, you're going to start to see why this is actually a linear equation and why this all makes sense. 1,000 is the starting amount, plus 1,000 times 0.07 is 70. And if you look, that's the constant amount in which the account increases in value every single month. That's the slope of the line, the rate of change. So it's as time increases by 1, So your months increase by 1, the amount of money in your account is going up by $70. Now, let's say we want to know how much money Alfredo has after 5 years. So let's say we let T equal 5 as an example. A of 5 is going to equal 1,000 plus 70 times 5. And if I calculate that out, that is $1,350. So let's go back to the previous page and check and see if that's actually correct. So after month 5, he should have $1,350 in account. So let's check that out. And after month 5, he's got $1,350 in his account. So sometimes it's nice to have a function, especially if we want to predict the amount of money that he's going to have in his account after a long period of time. So let's say we want to predict how much money he's going to have in the account after 24 months. Instead of having to follow that table for 24 months, we can plug 24 in for T into our function, and that'll tell us how much money he's going to have saved after 24 months. Okay, so that's an example of simple interest. So let's move our way down, and now let's take a look at compound interest. Now, compound interest is simply just an exponential growth model. So really, if you think back to the previous video, or actually 2 videos ago, I guess, y equals a times b to the x power is the general exponential function that we're going to use to model exponential growth or exponential decay. So again, this equation that we're given here for compound interest is kind of just one of those equations in disguise, and I want to break that down for you. There is a new variable that we have to take into account that's different from the previous example. So let's discuss what the variables represent first. A of t is the amount after time t, same as simple interest. P is the principal amount, same as simple. T is the time. R is the rate, again expressed as a decimal, but now we have a new variable, which is n, and that's the number of time interest is compounded per year. So you're going to hear terms like quarterly, that would mean that n equals 4. You're going to hear terms like interest is compounded yearly, that would mean n equals 1. Monthly, n equals 12. So you're going to have to determine what n equals based off of the context of the problem. So in this case, Alfredo's option 2, the interest was compounded yearly, so n would equal 1. Now, before we get into that specific example, let's kind of break down why this equation is just a y equals a times b raised to the x power. So again, a of t represents your output values, which is just y. In the equation, y equals a times b to the x. A is your initial amount. So in this case, p is the initial amount. So that really just represents what a is. 1 plus r over n is just going to be your growth rate because 1 represents 100% of the previous amount. Plus, you're going to get some additional amount, and that's your growth. That's your growth rate. So this would be b. And then n to the t is just going to come down or reduce to a power, so that's just to the x power. So y equals a times b to the x. So like I said, this compound interest formula is really just a y equals a times b to the x formula in disguise. So let's go back again and look at Alfredo's second option. So this is Alfredo option 2. So again, the principal amount was 1,000. So we started off with the same amount both times. The rate was the same, his interest rate was the same, so 0.07. But this time, he was earning interest on his interest, and the number of times that the interest is going to be compounded is 1. The time again was unknown. Okay, we weren't given a specific time, but we will evaluate this for a specific time later on. So here's our function. A of t equals the principal amount p, 1,000. So I'm just using the formula to the left, times 1, which is 100% of the previous amount, plus your interest rate over the number of times that interest is compounded is 1, and then raised to the nt, so the 1t power. So this simplifies down to a of t equals 1,000 times 1.07 raised to the t power. So as I had mentioned before, this really looks an awful lot like y equals a times b to the x power. All right, so again, let's say that we wanted to evaluate this for a specific time. So let's say after 5 months, we would do the exact same thing as before. A of 5 equals 1,000 times 1.07 raised to the 5th power. I did this out on my calculator and I got to 2 decimal places, $1,402.55. So if this formula works properly, we should be able to go back to the table that we generated last video. And after 5 months in option 2, Alfredo should have $1,402.55 in an account. Let's check that out. And he does. After month 5, he's got $1,402.55. So that's an example of how the compound interest formula will be applied. We have one more to go. And in this case, we're going to have to kind of jump back and forth between the computer and actually, I'm sorry, this screen in Desmos because I want to show you guys something graphically in case you get into a situation like this. So in your notes, I'm actually going to need you to flip to page 7 for this example. I'm sorry, not to page 7, problem number 7. Okay, so problem number 7. In this case, we're going to look at exponential decay. So we haven't looked at a decay model yet. So we're going to do that right now. If you look, all the variables are the same. Everything is identical to compound interest. The only difference here that you'll notice, you should notice, is this b value. So 1 minus r over n. So if you look, for compound interest, we had 1, which again represents 100% of the previous amount, plus some amount. So that's always going to give us a number that's greater than 1. And when b is greater than 1, that is an exponential growth model. If we look at exponential decay, I'll highlight a different color now just to emphasize what I'm talking about. Look at exponential decay. We're going to have 1 minus some value, which is going to give us a value that's less than 1 but greater than 0. So again, this will be some sort of exponential decay model. So in order to demonstrate this, what I'm going to do is I'm going to move ahead in the notes to problem number 7. So I want you to locate this problem. If I'm going too fast, you can just pause the video. But we're going to look at problem number 7 as an example. And again, part of this is going to involve using Desmos. So let's try example number 7 right now. This is an example of exponential decay. So Miss Picard wants to buy a 2018 Range Rover that starts at $62,500 for the basic model. The value of the Range Rover exponentially depreciates by 9.8% annually if it is kept in pristine condition and a normal number of miles are driven each year. Part A says write an equation that represents the value of this Range Rover depending upon the number of years that it's owned. Define your variables. B, how much is the Range Rover worth in 3 years? And then C, how long does it take the Range Rover to be half of its original value? All right, so this is going to use the exponential decay formula. A of t, the amount that it's worth after t, A of t is going to represent the amount or the value after t years. And then t is going to represent the number of years. Okay, what we also know is that the principal amount is 62,000. The initial value of the car is $62,000. We know that the rate at which it's depreciating is 9%, and we know n has to equal 1 because that's the number of times that the rate is compounding. Okay, it's compounding annually, that's 1. If this said quarterly, n would equal 4. If this said monthly, n would equal 12. Okay, so you have to make that decision based off of the context of the problem. So let's write an equation here. So a of t is equal to the principal amount, which is 62,500, times 1. In this case, we're subtracting because the value is going down over a number of years. It's the rate 0.098, which is expressed as a decimal, over the number of times that the interest is compounded, which is once yearly, raised to the nt, which is 1t. And if I simplify this down a little bit, I get a of t equals 62,500 times 1 minus 0.098 divided by 1 is 0.902, and that's going to be raised to the t power. Okay, so that's the formula that represents the depreciation or the value of the Range Rover over t number of years. So now what we can do is we can use that formula to determine the value or to predict the value after 3 years. So we're going to do a of, in this case, 3 is going to equal 62,500 times 0.902 raised to the 3 power, because we're replacing t with 3. Now, if we do that out on our calculator, we should get somewhere around $45,866.93. So after 3 years, the car has gone from being worth $62,500 to $45,866. So you've lost quite a bit of money there. Now, the next question says, how long does it take the Range Rover to be half of its original value? So there's a couple different ways that you can do this. I'm going to kind of do it the simplest way. So really what we're looking for is where a of t is half of 62,500. Well, half of 62,500 is $31,250. So I'm going to replace a of t with 31,250. And then the rest of the equation remains the same. We have the same initial amount. We have the same depreciation factor, and then t is still the time. So now what we're going to do is we're going to try and solve this equation algebraically. So I'm going to divide both sides. I'm trying to isolate t now. I want to find the time that it takes for the car to get to its original, or excuse me, half of its original value. So we're going to divide 62,500 on both sides of the equation, and we're going to get 0.902 raised to the t power equals 1/2. Now there's an issue here. You do not have an algebraic technique right now to allow you to isolate t. It involves using something called logarithms, and if we had more time this year, we would have learned about logarithms, but we don't. But what you can do is you can use Desmos to help you solve this equation. So what we're going to do right now is we're going to go to Desmos. And we are essentially going to solve a system of equations. All right. So the first thing that we're going to do here is we're going to graph y equals 0.5. I'm going to do actually y equals 1/2. So y equals 1/2, if I go back to this, is the right-hand side of the equation. So y equals 1/2. What we're also going to graph is this exponential part, y equals 0.902 raised to the t. So we're going to go back to that. Y equals 0.902 raised, in this case, I'm going to do it to the x power to keep our variables consistent. And now what you'll see is this blue curve shows you your first example of what an exponential decay curve is going to look like. So it's going to basically look like an exponential growth function, except reflected over the y-axis. So the way that we're going to solve this problem here is we're going to look for the point of intersection between these two curves. That will give us, the x-coordinate is going to give us the time, um, and then the y coordinate should be 1/2. It's the time that the car is worth half of its original value. So we'll click on the graph and you will see 0.291. Is that the right spot? Oh, you know what I did up here? I'm sorry, this should be 0.902. All right, that's better. Okay, so again, still an exponential uh, decay curve. I just typed it in wrong. So here, this is better. So if you look, you get 6.72 and zero point 0.5. So what that's saying is in 6.72 years, so that's your time t, the car will be worth half of its original value. So we'll go back here and we will write that. So in 6.72 years. So in situations like this, where you have to find a time. Again, typically we would have to use logarithms to solve a problem like that. What you're going to have to do is rely on the graph. So it would graph the left-hand side of the equation and the right-hand side of the equation using Desmos. So in this case, y equals 1/2 would be the right-hand side of the equation. Y equals 0.902 raised to the, in this case, we had to use x power would be the other side of the equation, and then we would look for the point of intersection of those graphs. In this case, you'd be looking for the x-coordinate because that's the time. For problem number 8, when you get to that, because you're going to have to do these problems for evidence of learning, part B, what I would suggest that you do is graph both of your equations that you generate, okay, and try to find the point of intersection on Desmos. That's a hint that I'm going to give you on part B. All right, so that's going to take us to the end of this video. I know these videos have been a little bit lengthy, but they are, kind of detailed, or the content's kind of detailed, and I want to make sure that you get all those details so you really understand what you're doing. If you have any questions or concerns, let me know. You can either email me or message me through Google Classroom. Otherwise, again, I hope these videos have been helpful. Good luck, and we will see you in the next video.